Hey everyone, Nate Bierschenk here. I'm the HB1100 service line sales lead as well as a general sales and marketing associate here at TerraTherm. Today's webinar is titled Introducing the IPTD Heated Box, or HB1100, a new thermal remediation approach for on-site treatment of contaminated soils and sediments. I need to admit that during the live recording, I forgot to press the record button until slide 3, and that's why this audio will sound a little bit differently. I recorded it after the webinar was presented, and that's also why I removed slide 2, which was basically instructions for attendees to follow if they had any questions that they wanted to ask during the Q&A portion of the webinar. You'll also notice that the Q&A portion was removed. We do this to protect the identity of the folks who ask the questions, as well as to entice people to attend the live webinar presentations. And without further ado, let's jump into the webinar already in progress. I hope you enjoy, and thank you for your interest in TerraTherm and our thermal remediation technologies.
Here's the agenda. We're going to discuss what is the HB1100, what are the benefits. We're going to go into the process overview, talk about the applicable contaminants, and then we'll get into the background on the technology and look at previous approaches of above ground treatment that we've attempted and implemented. We're going to talk about the Tier 1 treatment system, talk about the prototype heated boxes that we've made, and talk about the case studies. We'll also get into what we believe are the sweet spot applications for this technology, and then we'll run through an example demonstration project and also touch on the permitting and regulatory framework. So what's in a name? The HB in HB1100 stands for the heated box. The first one represents the first iteration of the heated box technology in the market, and the 100 following it represents the capacity of each heated box unit to treat 100 cubic yards of soil or sediment. And what about IPTD? This stands for in-pile thermal desorption. It's an ex situ application of our in-situ thermal desorption technology. Both make use of the principle of thermal conduction heating paired with vapor extraction. So there are different ways to configure IPTD, the details of which I'll touch on later on. And the HB1100 is but one approach of IPTD. So what is the heated box? The HB1100 is a cost-effective indirect thermal desorption technology for on-site treatment of contaminated soils, sediments, and debris. It's got patents in the United States and Canada, and additional patents pending overseas. And this photo that you see here is the pilot scale heated box at the ESMI facility in Fort Edwards, New York. And behind the heated box, you see this large thermal oxidizer that's used for on-site incineration and treatment of large quantities of soil that are trucked into this location. What are the benefits of the HB1100? It has a lower price than the alternatives, which include traditional on-site thermal desorption, over 10,000 cubic yards, and off-site treatment and incineration. Additionally, it eliminates the liabilities and risks associated with transporting hazardous waste through communities and manifesting waste and long-term ownership. Essentially, when you transport contamination to a landfill or something like that, you're just moving the liability from one place to another, and it's never really eliminated. It's a proven technology capable of treating organic contaminants to non-detect levels, and it's sustainable. We adhere to the ASTM greener cleanup standards. Additionally, transportation back and forth to a treatment facility is eliminated, which saves fuel and resources, And because the system is modular, all the components used in the treatment system are reused. So let's look at some alternatives for remediating contaminated soils and sediments. Right here, we're just looking at comparing incineration to landfill. We've got the HB1100 and stabilization and solidification. So the advantages of each are, does it reduce high concentrations of contaminations to clean? Of course, only incineration and the HB1100 would do this. Does it destroy the PCBs and all other organic contaminants? Again, incineration and the HB1100 are the only options. Can it separate PCBs? Only the HB1100 is capable of doing so. Does it immobilize PCBs and select organic contaminants? No. That would only be for solidification and stabilization. Is it effective across a wide range of soil and sediment characteristics? Incineration, landfill, and the HB1100 is capable of doing so. And is it effective on inorganic co-contaminants? No. That's the one case where the HB1100 doesn't seem like it would be a good fit. What's the process overview look like? So TCH paired with vacuum extraction. TCH stands for thermal conduction heating, and it's the process of heat flowing from a hot end of a solid object to the cold end. In our case, with HB1100, it's heater rods built into insulated walls. In soil or rock, the heat flows from our heater elements out into the soil by grain-to-grain contact in the soil and across solid objects and rocks. The fluids, such as the water, air, and napple, in contact with the solids also heat up at the same time. The heat moves out uniformly from the sidewalls and bottom of the heated box until the center of the heated box reaches its target temperature. As the soil is heated, contaminants in the soil are vaporized or destroyed by a number of mechanisms, including evaporation into the airstream, steam distillation into the water vapor stream, boiling, oxidation, and pyrolysis. The vaporized water, contaminants, and natural organic compounds are drawn by vacuum into our liquid and vapor treatment train. And this graphic right here is sort of a top-down view of the heated box. Imagine you're kind of hovering over, looking down, and each side, the left and right side, represents the insulated walls with the heater elements built into it. And then on the left-hand side of this table graph, you have temperature, and on the bottom axis you have temperature progression over time. So T1 represents initial heat up phase with the central area, the coolest area, and this of course is the area that we need to bring up to the target temperature in order to volatilize and capture the vapors effectively. T2 shows the second time interval being tracked, and you can see that the temperature in the central area is coming up in temperature. Right now it's at 200 degrees Celsius, but really what we're trying to do in this case, we're targeting a higher boiling contaminant, so we need the central area to reach 335 degrees Celsius in order to capture all of the vapors and effectively treat the area. And as a sweetener, because the process of TCH and vacuum extraction is so robust, it reduces or eliminates pre-treatment material segregation processes that a lot of traditional thermal desorption technologies require, and is capable of handling soils, sediments, and non-combustible construction debris, and even some boulders. What contaminants can TCH treat? Persistent organic pollutants or POPs, as John mentioned before, PCBs, and pesticides such as DDT, HCB, dioxins, or PAHs. It can also treat anti-organic contaminant, like we mentioned before, and it's even capable of treating mercury, as it has been demonstrated on a couple lab scale and pilot scale tests. So this slide shows vapor pressure versus temperature, and the contaminant property that is most dramatically affected by heating is vapor pressure, which rises exponentially with temperature. You can see here electrical resistance heating, steam enhanced extraction, and thermal conduction heating are all thermal remediation approaches, but ERH and SEE can only reach 100 degrees Celsius. So in that case, it's great for CVOCs. It can treat TCE or PCE, but for these other contaminants, you're going to need much higher temperatures, and only TCH is capable of reaching these temperatures for compounds such as naphthalene, mercury, PCBs, and PAHs. And once the contaminants are volatilized, of course, they're readily extracted as vapors. So there's two ways to apply thermal conduction heating. We've talked about the process. It can be done in place, in situ, using in situ thermal desorption, or it can be done above ground or ex situ with in-pile thermal desorption. Here is a summary of PCB treatment results using either ISTD or IPTD. These are a couple examples where we targeted PCB specifically. We learned much from Shell TerraTherm, who implemented the 5 projects you see here in the mid to late 1990s. At these sites, you'll see very high pre-treatment concentrations in milligram per kilogram. And in the second post-treatment, PCBs are all basically non-detect concentrations. Additionally, you'll notice off-gas treatment source tests are all well below the treatment standards. These are all very well documented projects, and many are available in the form of white papers on our website. So just let me know if you're interested in obtaining a copy, and I'll shoot them to you. This is a summary of dioxin treatment results using either ISTD or IPTD. We've got a Superfund site in Missouri, a Navy site in California, a project we did for Southern California Edison treating creosote contamination, but also dioxin, and a project that we'll touch on in a moment for the Ministry of Environment in Japan. And again, you can see the volume trees in the first column here. Pre-treatment concentrations are very high in terms of picograms of 2378 tetrachlorodibenzo-dioxin equivalents for toxicity equivalents, or TEQ. And the post-treatment concentrations within the soils are very low, and in fact much lower than the 1,000 picograms per gram target that applies to these projects. And the exhaust gases were monitored by independent third-party source tests and produced very low results in terms of nanograms per cubic meter compared to the standards of 0.2 nanograms per cubic meter that apply to the U.S. projects. And this is a demonstration of a photo of the thermal blanket that Shell TerraTherm implemented in the late 1990s. And I'd just like to show this because it does a really good job of showing what thermal conduction heating does to the soils. Here we have post-treatment soil where we were targeting 300 degrees Celsius to treat halogenated SVOCs and PCBs, and you can see the remaining soil around it is still contaminated, but just look at how clean that soil looks, and that's what we're using. And then this is an in-pile thermal desorption demonstration that we completed in 2009 with our partners in Japan, Shigotech. And this is treating dioxin contamination in a small demonstration scale box, sponsored by the Ministry of Environment of Japan. The project was highly scrutinized by the Japanese government and academia, and it involved placing 1 cubic meter of heavily contaminated soil within a box insulated on the top, sidewalls, and bottom, into which heater wells are installed, with the resulting off-gas treated with a thermal oxidizer, a heat exchanger, activated carbon vessels. These here are the blowers and the stack. This slide shows a site plan where the project was implemented, and the project was operated under a tent, which is represented by this blue box here. The letters shown, A, B, C, and D, around the perimeter are where the ambient air was measured before, during, and after the project's implementation. You'll see that during the demonstration, ambient air concentrations did increase slightly, but remained well below the environmental standards of 0.6 picograms of toxicity equivalents per meter squared. And then this slide just shows the effectiveness of this technology with the soil concentrations before versus after heating. And then, of course, you can see the dioxin concentrations before remediation and after. And the Japan standards are 1,000 picograms per TEQ per gram. And you can see it's much below the Japanese standards. And then following this project, IPTD became approved for treatment of dioxin-contaminated soil or sediment in Japan. What you see here is a configuration of the IPTD that some of you may be more familiar with. You'll see an insulated pile structure with heater borings installed vertically, just as they would be implemented for in-situ thermal desorption. All the same heating principles remain, only the geometry or the configuration really changes. This is the same configuration that we implemented at the Da Nang airport in Vietnam. Here's a picture of the IPTD thermal treatment pile and the liquid vapor system that we're implementing in Vietnam. It's at the Vietnam airport, and it's an Agent Orange hotspot, legacy from the Vietnam War. TerraTherm is the prime contractor, with the remediation overseen by CDM Smith and funded by USAID. So as you can see, this is a very large mega project treating 190,000 square meters with a total volume of 70,000 cubic meters. Due to the massive amount of soil requiring treatment, the project was split into 2 phases. The area shown here in yellow covers 40 acres with the contamination relatively shallow in terms of average depth. Thus, it wouldn't have been feasible to treat all of this in situ. So the phase 1 is complete, with phase 2 taking place later this year. This table just shows what the pre-treatment concentrations of dioxin were, and then the Vietnam standards. Soil samples collected over the entire range and depth of the pile concluded that mean post-treatment dioxin concentration was 8.9 nanograms TEQ per kg, well below the 150 nanograms per TEQ per kg. So we were well below the treatment goals. This is just a process overview. As you can see, we have 1, 2, 3 heated boxes in one array. The lid of box 3 is off to the soil to allow for filling or removal. Here is an SCR cabinet and the Tier 1 treatment system in the back. It's a scalable technology, meaning multiple units can be deployed for larger treatment volumes or for expedited schedules. It's mobile and modular and features plug-and-play equipment components. And as we've mentioned, it's proven through 16 years of 100% treatment successes and 50 sites closed worldwide. We can guarantee 99.9% removal efficiencies. And of course, it makes use of the centralized treatment equipment, which provides efficient utilization of equipment and labor by treating batches in a sequential, staggered operation fashion. And I wanted to show you real quickly a 360-degree view in this nifty panorama that our CAD department put together for us. And as you can see, the electrical components here. And again, here's heated box 1, 2, and 3 with the lid of the third box off for filling or removal. The vapors follow this vapor manifold once they're extracted from the heated box. And it is brought into our treatment system. In this case, we're making use of the Tier 1 treatment system. Following the vapor extraction pipes, once we enter the Tier 1 container, you can first see the condensate separator. Looking down further, you see the heat exchangers, which are supplied by the chiller or cooling tower over here. Here's the moisture separator. Blowers are right here. And then the vapors are taken out of the unit. And you'll see the vapor phase carbon GAC vessels and the stack that blows the vapors out. A thermal oxidizer could be substituted for the GAC if required. And the second container back here is not shown, treats the liquid condensate through GAC. So we're shying away from custom-built process equipment for each and every project because custom jobs rack up not only engineering time, but logistical and operational resources as well. You see here a conventional approach where we have all of our process equipment out in the open looking somewhat messy, but with our Tier 1 treatment system, which I'm trying to plug, we are moving from something that looks like this to this. It's a modular plug-and-play treatment system that comes ready for quick hauling, construction, and operation. And the purpose of showing this to you is to provide some context as to how projects have traditionally been operated with how we have moved now to a more standardized, lower price approach. And it's important to note that the Tier 1 treatment system is not mutually exclusive to the HB1100, but it can also be utilized on all modest-sized projects. Certain HB1100 projects may make use of other pre-existing skid-mounted equipment, including a thermal oxidizer as required. The HB1100 prototype, as John mentioned, was developed in partnership with ESMI, and the pilot test was implemented at their facility in Fort Edwards, New York. Both pilot tests were implemented under New York DEC oversight, and the purpose of these pilot tests was to confirm design effectiveness. We had two pilot tests. Pilot test 1 was treating VOC and light end SVOC contaminated soils, in this case PAHs. And test 2, we were treating heavy end SVOC contaminated soils, in this case MGPs. And this table here that you see is from pilot test 2, and it shows some select contaminants with their pre-concentrations, the goals we were trying to reach for unrestricted land use cleanup goals, and whether or not we met or achieved the cleanup goals. And of course, we have yeses across the board. composite soil sample results showed treated soil is suitable for unrestricted use. Depending on the contamination, we found that for the pilot tests, 28 to 32-day treatment duration was appropriate. And these pilot tests only treated 60 cubic yards or 90 tons per batch. And in pilot test 2, we reached temperatures up to 368 degrees Celsius. So what are the sweet spots? We think soil volumes between 2 to 10,000 cubic yards are appropriate for the HB1100. Anything more than that, you might be looking at a larger scale IPTD approach. It's for sites with contamination accessible by excavation, obviously. And again, for VOCs, SVOCs, pesticides, PCBs, and mixed hazardous wastes. And also, the further the site is located from a hazardous waste landfill or a RCRA treatment facility, the more attractive this approach looks and is. Other applications that we're thinking about for the HB1100 would be for on-site alternatives for IDW, such as drill cuttings, for an example, RCRA hazardous wastes, corrective action management units, or CAMU, and treatment to universal treatment standards for land disposal restricted wastes, or land banned waste. Now we'll get into an example system description and the parameters. In this case, we're looking at treating VOCs with 12 boxes, each box capable of treating 100 cubic yards, and total, the soil volume that we're trying to treat is 1,100 cubic yards, 11,000, excuse me. Tonnage per box is 140 tons. 100 degrees Celsius is the target temperature, and the duration per cycle is 15 days with 10 cycles total. So it takes 15 days to load, heat, cool, and unload each box per cycle, with 10 cycles overall, and 22 weeks for the operations duration. Mobilization and construction takes about 2 weeks, and demobilization another 2 weeks. Here's an example system concept. The heated boxes will be running simultaneously as 3 boxes are anticipated to be loaded and started every 2 days. And here is the preliminary division of responsibility. TerraTherm assumes that the owner and consultant will excavate the contaminated material, remove logs and debris 2 feet and up, and stockpile to allow drainage to less than 20% moisture content, which involves keeping the stockpile covered. TerraTherm will fill and empty the treatment chambers with an excavator or loader, and it takes approximately half a day to 1 day per chamber to fill or empty to an adjacent clean stockpile. TerraTherm also assumes that the owner or consultant will obtain permitting with TerraTherm support, furnish electric power and gas, and perform confirmatory sampling and analysis of the treated soil. Here's just a slide that shows what our estimated costs are. In this case, the COCs averaged 66 ppm, 11,000 cubic yards of contaminated soil and sediment, soil moisture content to 18%, wet density at 1.5 tons per cubic yard. Power costs are 15 cents per kilowatt hours, and here is where we would enter the total required electrical service and the overall electricity consumption. We'll provide costs in either cubic yards or tons, and also provide a total lump sum turnkey. So what does the permitting look like? We've got a permitting support team, including Nick DeLeon from Cascade, and a number from ESMI Associates as well. It's very similar. It's the same process as our in-situ projects. You know, we need vapor and liquid discharge permits, among other standard construction type permits. State regulated sites, CERCLA or Superfund regulated sites. We're going to need the equivalent permits for that, as well as for RECRA regulated sites, and it could be permitted as a CAMU option, as well as PCB or TSCA regulated sites. And again, just to surmise why HB1100, it's a patented, robust technology, and it's sustainable as well. It's customizable to treat the entire range of organic contaminants. Use it for on-site treatment of listed and characteristic land disposal restricted hazardous wastes to the applicable cleanup goals. Reduction or elimination of liability and lagging costs tailing from alternate solutions. And TerraTherm offers an experienced professional team with highly successful track records of delivering projects on time, on budget, and safely. And at this point, I'm finished with my presentation, so we can start answering any questions that you guys may have.